All right, greetings, scholars. We still got about a little over 7 minutes, before class starts. So this is a good time if you have questions, ask questions. If there aren't questions, I'm gonna just kind of fill the space with some gaming content. Maybe if you can hear me, if you're on this call, you can pick between any of these four games, 1, 2, 3, or 4. One is Mobile Legends.
Play that Naruto. That's Naruto.
Okay, we'll try it since you requested it. I haven't played this game in a minute though. Let's see. Siri, set a timer for 6 minutes.
6 minutes starting now.
What notifications? I'm gonna put don't allow. Yeah, it's been a minute since I played this game. So I stopped playing. Like I was trying to max out like one of the Narutos, whichever one of them. And then the next person that came out was a Sasuke, and this was months ago. Next, not to track. Come on, not to track. I don't even know if it's gonna allow me next. Not to track. Yeah. So, like I said, it's been a minute. This game is, it's kind of like, I don't know how to describe it really. It's because it's not really. At first, I was thinking of not Naruto. I was thinking it was like Mobile Legends. But it's like you're going against the computer. There are some live teamwork with people. It's just and then like I said, I was trying to make up cards. Learn. And it still wasn't that. And what I thought I was buying, I thought it was going to be. I mean, that was kind of cool. I kind of wanted to see the end of it.
Naruto Cross Volto Ninja Voltage.
I got a lot to do. I stopped kind of towards the beginning of Naruto before I did know. That sucks. That's how long this been since I've been. So it's on here, but for whatever reason. They closed out some really good games. Like this was a fun game. It's still on my device, and maybe one day they'll open it back up. Right now, I can't access it. They did the same thing to Mobile Legends. We got like 5 minutes. They did the same thing to Mobile Legends, but Mobile Legends is now at a point where you can play like kind of like before, but you can't buy anything. Like it's not linked to the store. So if you've already had it on your device, then you can play kind of like before, but you're locked into whatever skins and whatever you had before. But if anything costs diamonds, once you run out of diamonds, that's it. And I'm out of diamonds. So let me see. We still got at least 4 minutes. Okay, so this Frontiers game, what this is like Apple version, you know, like when you have the Apple One or whatever, it comes with the Apple Arcade. So this is the Apple version of Tower Defense. I'll do a little bit more of this for a few minutes. So it's fun. Like I like Apple Arcade. I don't like that it's a monthly subscription, but I mean it comes with everything. It comes with like all the stuff that the Apple One or whatever. But I do like that there's no commercials, you know, for all their games. It's the full version of everything. No ads or anything like that. And you know, it's just fun.
Professor C.
Uh-huh.
I had another meeting I had to get on for at 6:30, but I still wanted to join class and get credit for the attendance. So what do I do?
Hey. What's your last name?
Simpson.
What time do we get out? 30 minutes? I don't know. I won't mark you as absent. I might mark it as like excuse or something. And so you don't have to stress. The only thing with attendance, you just got to make sure you're not marked as absent. As long as you're not marked as absent, then you're good to go. So yeah, don't worry about it. Just just discreetly excuse yourself when it's that time. Yeah, and just thanks for giving me a heads up. And I at least won't mark it as absent because that's the thing, you don't want to rack up unexcused absences. We still got like 2 minutes. My timer should be going. Let me see. Siri, change the timer to 2 minutes.
Okay, 2 minutes. Counting down.
So this is the stage I've been working on. I'm just going to try to do a speed run. So I'm going to position him here. I'm going to go ahead and start these guys because I don't really have time. And so these ghouls, they're kind of fast moving. I just dropped all my resources on them kind of quick. I'm trying to think of my setup I used to do. Oh, speed run, let's go. I can't even tell you. Let me drop some more of these guys. So I'm building mage towers. I just forget my little initial setup. I know it was a bunch of these guys, and I don't really remember exactly where they were. I'm gonna try to max this one out. They give you like some gold up front. I like this one for this stage, and I think I'm gonna max out this. Okay. What's the time? And so like obviously we're not, and so I'm kind of cutting them off, the little wave, the early waves anyway, or at least trying to. And it's basically a tower defense. And so I'm focused on trying to build mage, like they are just blowing through. Back him up some. I think once I get to the second wave, then but I don't think we're gonna have time to go that far. I'm gonna go ahead and drop this. Okay, I think that's it. I'm gonna go ahead and put him back. And I think that's it for now. I think we're gonna run out of time. So there are like 3 different paths where they just start swarming, and I'm trying to defend 2 exit points. These 2 points coming to the left of the screen on this stage. I think this is the quote unquote strongest hero on this game, but I still can't get. I've beat it like maybe once or twice, but I can't get like 3 stars, and that's my time. All right, Siri, stop. Anyway, that's a little bit of tower defense. Like I said, we didn't really have time yet. We got 30 seconds. Okay, that's close enough. So we'll give people 30 more seconds to get in. I'm trying to keep an eye on my timer here. Siri, turn the heater off. Let me grab this guy. Here. Let's go. Here. Join.
DJ last night too. Yes.
Join. Come on.
Some people take it worse than others.
Okay. Let me go through the announcements first, and then I'll check the chat. I saw that notification there. Let me see. All right, gentlemen. So welcome. This week we are approaching the culmination or the end of Chapter 2, which means we can anticipate Exam 1 to become available. It should become available this upcoming Sunday. I usually schedule exams to become available on Sunday mornings at 11:11, and it's due 7 days later, essentially, a little more than 7 days later at the start of class on that Monday, 7 days after that Sunday. So again, you can expect Exam 1 to become available this Sunday. Unlimited attempts, the system is set to take your highest score. And for this first 7 days, you can earn up to 100%. I want to say after the due date, there's a late penalty. It's either 5% or 10%. It's still unlimited attempts after the due date, but then again, there's a late penalty. So we're going to go ahead and get started with Chapter 2. Section 2.5. Let me check the chat. Anything else? Yeah, I think that's the long and short of everything. Oh, good. So we were in sync. Yeah. So, and then also I kind of check the grades. So, just check your grades in Blackboard and make sure they look accurate. It should update automatically. I don't really think that there's anything for me to do per se. So I just kind of glanced at them. It looked like it was populating. I linked it, and I tried to set it up where it would update your grades automatically, like a live update. So, as you complete assignments, it should update in Blackboard. And I want to say it's accurate. It should be accurate, right? So, again, it's a good idea to check your grades in Blackboard for accuracy. If anything looks out of order, just bring it to my attention maybe at the end of class, or email me, or don't hesitate to call or text either. If just anything looks out of order. But again, it should be automatic. Okay. I'm gonna grab this. Get ready to go. Ready to rock and roll. Okay. Yeah, I think I'm streaming. Let me check. Yes, it's live, so it's about the best I can do. Okay. All right, so continuing chapter 2 on exponential and log functions. So we have been applying the derivative to exponential and logs. I think with the beginning of chapter 2, we reintroduced or revisited the concept of exponential and logs from College Algebra 2. Just some properties and concepts there. And then for the derivative of the exponential, so we started with the e to the x exponential. We started with that case because it's a special case or a unique case of a derivative where the derivative of e to the x is e to the x, right? So e to the x is its own derivative. That's a special property. I don't think we've gotten into the general derivative, but I mean, if it pops up, we'll go into those details. So then after exploring the derivative of exponentials, we explored its inverse, which are the natural logs, right? So the derivative of natural log, du over u, or f prime over f, right? So, that's essentially the derivative of natural log, and we explored some concepts there. So here with section 2.5, we're going to be looking at some applications with exponential decay, okay? Objectives here: 1, find a function that satisfies dp by dt equals negative kp, convert between decay rate and half-life, and solve applied problems involving exponential decay. So I think last time we said a function satisfies this expression dp by dt equals, now I think last time it was just kp instead of negative kp, if and only if p was an exponential function of the form basically pert. It was, basically, like p naught times e to the kt from last time. Yeah. So we're going to see how, when we're talking about exponential decay, how this negative changes that expression, all right? So this equation, dp by dt equals negative kp, it's kind of a repeat from last time. It's just that we have dealing with that negative, where k is positive, shows p to be decreasing as a function of time, and the solution, this is the PERT that I was talking about. P of t equals p naught e to the negative kt, right? So notice that this one is similar to what we talked about last time. Again, we just introduced a negative. And notice here for the p of t, we introduce a negative in that exponent as well, right? So when we're doing this exponential decay, we put a negative in power, and our k is positive, right? So we're letting k be positive, and we put the negative in the power there. This shows to be decreasing exponentially. So this is an example of exponential decay. The amount present initially at time equals 0 is p naught, right? So p naught is our initial amount or our starting amount, okay? So let's just kind of go forward with it. It's kind of a repeat from last time with the exception of the negative that we're introducing in those two locations, okay? So exponential growth is like what we did last time, what you see on the left. P equals p naught e to the kt. It's kind of like PERT, p, where the r would be our rate. In this case, they're expressing the rate as k. But exponential growth is like what we have on the left. And so today we're going to be looking at exponential decay, right? Things that behave in that manner as on the right, okay? Notice that everything's the same. Our k is positive in either case, but the exponent is negative for exponential decay. All right, so then we have the decay rate k and the half-life t are related as follows. So the rate times the half-life equals the natural log of 2. I think I used that last time. The main one that I use, I think, is like the bottom one. The half-life equals the natural log of 2 over k. Okay. So again, the half-life, or the capital T, equals the natural log of 2 over k. Okay. Okay, this is fine. All right, so let's in this example, we're looking at plutonium-239, a common product of a functioning nuclear reactor, can be deadly to people exposed to it. Its decay rate is about 0.0028% per year. What's the half-life? Okay, well, they gave us the rate. If we just use what we had on the previous slide, let's see if that works. I don't see why it would. Okay, so from the previous slide, we just said what the half-life equals the natural log of 2 over k. This is my table is like extra noisy today. Okay, let's see if we have this. It says, what is the half-life? Okay. So then the half-life should be the natural log of 2. What's the rate? See, so this one is amicable because they gave us the rate, right? So it has a decay rate of 0.0028% per year. So we need to convert that percent to a decimal. When we're doing these calculations, we need to make sure that it's in decimal format. So to go from percent to decimal, we just move the decimal place to the left 2 spaces. So then we got 000028. Then from there, it's just a calculator problem. Okay. So if I can pull up my trusty dusty rusty. Let's do another page. Justified. Okay, you look good. Reload and refresh. Okay. All right, right there. Come on. All right. So I'm just going to hit natural log of 2 divided by 0.0000028. Okay. So almost 25,000 years. So after about 20, like you'd have to wait nearly 25,000 years for half of plutonium-239 to persist. So we're going to say, or in that amount of time, half of it will have decayed away. 24. Let's go 2565. 755. Let's go 2565. Years. So after nearly 25,000 years, half of plutonium-239 would have decayed away, and half would remain. At least that's what we're seeing here. Okay. So approximately, yeah, same thing we got. Okay. Okay, that wasn't too bad. Quick check. I usually leave as an exercise. Now, let's see. I guess, yeah, if we get through this quick, well, we can work on the back end. All right, let's look at this example. So the radioactive element carbon-14 has a half-life of 5730 years. The percentage of carbon-14 present in the remains of plants and animals can be used to determine age. Archaeologists found that the linen wrapping from one of the Dead Sea Scrolls had lost 22.3% of its carbon-14. How old was the linen wrapping? Let me think. Okay, we got a half-life. So that can give us something about the rate. Okay, all right. I feel like I need some more space. So I'm going to kind of work here. I think there are 2 formulas that's going to be at play here. Half-life formula, natural log of 2 over k, and then the exponential decay formula, right? So then like P of t equals P naught times e to the negative kt. Actually, lowercase t, right? How old? So we're trying to solve for lowercase t, right? It says how old, so we're trying to solve for lowercase t. So we can use the half-life to find the rate. Let me see. Starting amount. Radioactive element had a, okay. So, it lost 22.3%. So say it started with 100%, then it's going to finish with 100 minus 22.3%, right? So that's how we're going to do that. Let's go ahead and find the rate. So we can isolate the rate. Our k is going to be, it should be the natural log of 2 over the half-life. So that's going to be the natural log of 2. The half-life is 5730. Okay. So I'm going to leave that for now as our exact answer for K. I could crunch it, but it's going to spit out some long decimal that I don't feel like writing repeatedly. So I'm going to just reference this. I'll reference it as a star for now. So when I go to use K, I'm going to use that calculation there, okay? So now if I want to solve for T, I probably should give myself some space. I'm going to try to work here for now. Okay, I put my equal sign here. Again, if we started with like 100, like 100% of some unknown amount, e to the negative our K, I'm just going to reference it as star, and we're going to solve for T. So again, we start with 100%. It's lost 22.3%. So what is that? 87, is that 87.7%? So 0. Of P naught. All right. Hey Google, what's 1,000 minus 223?
1,000 minus 223 is 777.
Okay, so 777. I think I made the mistake before. Yeah. That's a 7 there. Okay. That makes more sense. Yeah. So again, we're using two formulas here. We use the half-life formula, right? They gave us the half-life, so we kind of cross multiply to isolate the K. So then we have an expression for K. Then we use the exponential decay formula, and I think we have everything because we can divide both sides by P naught, right? That's going to be constant. So if we divide both sides by P naught, they're going to cancel each other out. So then again, we started with 100% of P naught times e to the negative K. I'm just referencing my formula on the side times T. We're going to be solving for little t. And then again, if we started with 100%, we deduct 22.3%. So we finished with that 77.7% expressed as a decimal. So from this point, we have one unknown, one equation we can solve, right? There are no more unknowns at this point. Only unknown is the lowercase t, okay? So at this point now we can take the natural log on both sides, right? Natural log of this, natural log of this. Now when we take the natural log of the right, this is going to cancel this, and that allows us to bring the power down in front, okay? So let me kind of update where we are at this point. Okay, I'm going to go ahead and solve for t, right? So then t is going to be equal to the natural log of 0.777 divided by negative k. I'll write it like this. Natural log of 2 over the 5730. All right, so that's an exact expression. So again, I just did algebra. Again, to get that expression out of the exponent, I took the natural log on both sides. The natural log on the left persisted, right? The natural log on the right cancels the e, and that allows us to bring that power down on the same level as everything else. Then, if we just want to solve for t, we isolate the t by dividing both sides by negative star, and that's where that denominator came from. Okay, so from here, it's a calculated problem. Okay, so again, I feel like it might be challenging to follow what I'm doing, every minute detail. If you can just get the gist, like, okay, you can see what formulas I'm using for this example. You see that, okay, I started with the half-life formula, and then I used algebra to solve for the missing unknown. I found my rate. And the other takeaway is, if you do write out that decimal for the rate, you got to write out the long decimal every time until you get to the end. You only round at the end. If you round early, like in your calculations, it's going to make your final answer more and more skewed, and you won't be able to get it right. And you're going to kind of be like, why can't I get this right? So again, with these calculations, you either have to keep it exact in a similar to how I did, or if you crunch a number along the way, you got to write out that long decimal every time you use it until the very end. Only round it at the end, right? Otherwise, it won't work, right? Okay, so let's crunch this number. The numerator is the natural log of 0.777. Divider, I'm glad I checked that number. I was like, because the only reason I checked it because I remember I made a mistake. I couldn't remember what mistake I made, but I knew I made a mistake when I did it years past. I was like, let me just check and make sure I did the number right. I was like, oh, that was the same mistake I made before. Anywho, natural log of 2 divided by the 5730, you got to watch your parentheses here, okay? So this should close off the denominator. Let me see. Yep. I think we're good. So now, how old are they? 2,000 years old? Dead Sea Scrolls? Okay. I'm going to say approximately 2086. 2086 years old. Okay, I think that's a reasonable result. Let's see, how do we do? Okay, so again, they crunched the number. They essentially wrote out their long decimal. They got the natural log of 2 over the 5730. Then they used basically the PERT for exponential decay, right? So the future amount equals the starting amount times e to the negative kt. I think we got the same thing, 2086, approximately 2086 years old. So hang on. Sorry, guy. Wrong person, wrong. All right, so yeah, 2086 years old. The linear rapid from the Dead Sea Scrolls is about that. That's exactly what we got. Okay, so give me just a moment. I feel like there should be questions, but give me a moment. Okay.
I really would be excited to do this.
Guess you guys are kind of okay. So let's keep going. Quick check. I'll leave as an exercise for you. We are moving and grooving. Let's keep going. So example 3. Following the birth of their granddaughter, 2 grandparents want to make an initial investment of P naught that will grow to $10,000 by the child's 20th birthday. Interest is compounded continuously at 4%. What should the initial investment be? We're going to use, this is the PERT formula, P equals P naught e to the KT. Again, I'm saying PERT because usually for K, I usually use an R, but this is fine. It says, so we're trying to solve for P naught, okay? So if we want to solve for P naught, we got, the only thing we're not going to know is P naught, right? So we have our variable times some number, right? We have our variable times a number. So if we want to solve for that variable, we use the inverse operation, right? So in other, long story short, we can say that P naught equals P divided by that number, whatever that number is, right? So again, divide both sides by that number. So that means that P naught is going to be equal to P divided by E to the KT. Let's plug in what we have. We want to finish with what, $10,000, right? E, what's the rate? 4% as a decimal, 0.04. 20th birthday would be 20 years. So again, we have everything. We isolated our known, so we just crunch it in the calculator. Now, come on. Let's see. So we're going to do 10,000 divided by E 0.04 times 20. Okay. So just shy of 4,500 is what they should start with. Like if they start with 4,500, then by the time with this account, let this account run for 20 years, then when that child becomes a 20-year-old, they'll have at least that amount in that account. 4% is actually decent. I know I could work wonders with a 5% interest, steadily growing. I was like, so that's one of the things that I play around with. Like sometimes videos will pop up in my YouTube feed talking about what would it take so that you can like retire on like dividends, right? And long story short, I forget the rate, but they were talking about like, a company that's, low risk. It's established. It's been there for like 50 odd years, something like Coca-Cola or something. Again, I'm no financial advisor. So you got to do your own research, yada yada yada. But they were like, you get something like that, and you invest, and like he was like, if you invested. Now, when I did the calculation, it was anywhere from like $200 to $300 a month for like 30 years, and whatever returns or dividends you've earned on that account, you just reinvest it back, and then within 30 years. You honestly be a millionaire. You'll be bringing in like anywhere from like at least like 5,000 a month, if not more, just on dividend returns, something like that. Again, I'm no financial advisor, but I like the concept because $200 a month or $300 a month, Lord knows. Like I told you, like at the opening of the class today, lecture, I was like I splurged on that Naruto game at least $100 at a time. And I could take some of that and invest it into something like that where it's like dividends and just reinvest everything back into that account. And then within 30 years, by the time I get to retirement age, even if I wasn't working like for a company, I would have built my own retirement. Just staying true to that. It's kind of like a car note or anything, but instead of paying for a car, you're buying into like a lifestyle. You know what I mean? And that's just one thing. I can have other things that I'm working on in the interim. So I think it's something that's worthy to look into. If you have an advisor or somebody you can talk to, that's great. YouTube, I mean, it's all laid out in there on YouTube, but again, it comes with some risk and this, that, and the other, and so that's why it's good to have like a live person that you can chat with about it, especially coupled with like AI and like ChatGPT and DeepSeek and all these kind of things. Like there's like what you can do is nearly unlimited. If you really, I feel like I know I struggle with personally is it's less about the result that I'm getting and it's more about I'm probably not asking the right questions. You know what I mean? Like if you're not asking the right questions, you can have the answer right there in front of you, and it won't mean anything because you're not looking for it. You know what I mean? So I play around with that a lot, and so I started like looking into like options trading and all this kind of stuff. That stuff is so interesting and it makes sense. Like I'm so excited. Like I was like, okay, I was watching this one today. This guy was using this like options trading strategy that had 4 different parts to it, but it made sense if you set it up properly. It's designed for like stocks that you think are just going to move sideways. If you think it's not going to go up, nor it's going to go down. And so his strategy is based on a stock moving sideways. And he was like the probability or the likelihood of a stock moving sideways, is much higher than, you normally with options trading, you have to decide, okay, is it going to go up within this time frame or is it going to go down within this time frame? And then there are strategies where it's based on, well, we just need the stock to move. We don't care if it goes up or down. As long as it moves, we're going to make money, right? So in my mind, I'm thinking, it's like, okay, I know there are strategies where as long as it moves, you make money. This guy today just showed a strategy where as long as it doesn't move, you make money. So I'm like, is there a way you can pick those two together so that it feels like you're guaranteed to win? But it's like, again, that's a feeling. I'm not an advisor. You gotta assume all the risks and all this other kind of stuff. And so that's what I'm gonna be playing around with. Like I was like, I wonder if I can get this to work. I liked it because it was manageable. But one caveat that he did mention kind of towards the end of the video, he was like, but you do have to be careful because different brokers have like commission fees and things like that, and that might thwart your efforts. But it's exciting because honestly, I mean, young people, they had no schooling, no education, no nothing, and they broke free in that realm. I mean, like they went from like $30 to financially free. Now, I mean, again, $30. If I'm splurging on like games, I could take a fraction of that and start playing around. You see what I'm saying? And just do my research and this, that, and the other. So, okay, enough of that fun little adventure. Let me go ahead and crunch this number. But I just, I mention it because this is a math class. We're talking about finance and stuff like that. Business, 1, 2, 3. Did I already crunch this? I think I started. That's fine. I'll just go. I think I did. Let me check. Here it is, right there. Okay. Yeah, I'll have to take care of that momentarily. Okay. That's 44 or so. What is that? 29 cents. So this is approximately 40. like I can kind of talk a lot about, and I do kind of want to just kind of share my experiences when it comes to studying finance and numbers, because I study numbers all the time and like rates of change and patterns and things of that nature. But then you couple that with like the markets, stocks, cryptocurrency, and forex. Man, and so that all that realm is just all about pattern recognition. And so like people talk about like candlesticks and how to read them and following trend lines. And I'm telling you, these people like they don't be bright. Like we be way smarter, but I think that they're more willing to take certain risk in certain areas, and they get free. So I was like, okay, well, but it gives me confidence because it's like, okay, if you do it, that means I can do it too. It's just a matter of time. It's not a matter of if, it's a matter of when, right? 44, 93, 29, right? Exactly what we got. They don't know any of this stuff. Not that it's, I mean, this kind, I feel like this discussion is more like if you wanted to get into like any kind of creation, like coding, or if you wanted to study like analysis of systems, like queues and like, okay, city planning, like if you're building like stuff like that, then this kind of stuff comes into play. And even if you don't know it, it helps to be aware of it, it just helps so that it's not so foreign and intimidating. A lot of times people see stuff like this and they shut down and they don't even try. But if you at least have some command or something like this coupled with what you're naturally, been studying or what you're naturally good with, then it gives you an edge over other people. You know what I mean? It makes you more marketable. If you had two people that were applying for your job, they both were qualified, but one had a decent command of mathematics, knowledge, and content, and other was like completely inept in that regards, then obviously one would have an edge over another. Okay. So let's look at this guy. So present value, P naught of an amount P due T years later at an interest rate K compounded continuously is given by this. The present value, let me think. P naught equals E to the, okay. So all they did was take the PERT formula, P P equals P naught E to the KT, and they just solved for P, right? So remember they solved for P naught. So I think in the last example, we said we had P naught times some number. We divided both sides by that number, and this is exactly what it gave us. We wrote it as a fraction form, but this is the exact same thing, just with a negative exponent instead of writing it as a fraction. So the technique that we literally just used in the previous example, this is like summing it up into a formula. Again, you could just use PERT and do what we did in the previous example, which I feel like is better. You kind of get 2 for 1. The one formula, as long as you do a little bit of algebra, you get both of these guys. So whichever you resonate more with. Okay, let's keep going. So then here we want to take a look at Newton's law of cooling. So the temperature T of a cooling object drops at a rate that is proportional to the difference T minus C, where C is the constant temperature of the surrounding medium. Okay, so capital T is the temperature of a cooling object, and then C is the temperature of the environment. Okay, so then the rate of change of the temperature of the object over time is going to be given by this negative K times T minus C. The function that satisfies the above equation is this A times E to the negative KT plus C. Okay. So basically, when we take the derivative of that bottom function, we get the above function. That's fine. Okay. All right, let's keep going. So we're just gonna use this. Like I don't expect you to commit any of this to memory. We just need to know how to use it. Okay. So a body is found slumped over a desk in a study. So now instantly my mind is like whisked to like, I don't know if you ever heard of like Hercule Poirot, those movies like The Detective, him or Miss Marple, these BBC detectives or whatever. Or is it BCC? I don't know. But yeah. So they, Hercule comes in and discovers a body is slumped over a desk in a study. A coroner arrives at noon, immediately takes the temperature of the body and finds it to be 94.6 degrees. She waits 1 hour, takes the temperature again and finds it to be 93.4. She also notes that the temperature of the room is 70 degrees. When was the murder committed? Ooh, okay. I kind of do need some space on this one. And I kind of needed the formula. All right, let me see. I can pull a page here. This is slide 20. So I'm gonna copy this. Hopefully this works. Sometimes it don't work. There it is. Paste. Nice. Okay. So then I want to just get a copy of these formulas. I just want it from here. Copy of this. And I'd like to duplicate. There it is. Crop. Crop. This one. Okay. So we're going to use these two formulas here. All right. Let's pull a copy of the information that was given. She finds the temperature of the body. So what is that, capital T? To be 94, or at the initial temperature, 94.6 degrees. And then the temperature of the body 1 hour later to be 93.4 degrees. And the temperature of the room to be 70 degrees. Okay. So then we want to solve for little t. Let me pull this, cut, paste. Okay. So this is the information that was given. Okay. All right, so we have two different temperatures. We have the temperature of the room. We're trying to solve for little t. So it looks like we need to solve for A and K. Let me see if we can plug in. Does it tell us anything about A? Back. Let's see, is that, we consider that to be the initial, the rate of change? Okay. So let me see. Okay, so it looks like from our T of T formula, the temperature, the formula for the temperature of the body. If we, like, for instance, if we plug in the initial temperature T naught, it looks like we don't know A and we don't know K, right? So it looks like we have two unknowns, so that's why we had at least two pieces of information. Let's plug in what we have, right? So again, we don't know A, E, we don't know K. Oh, wait a minute. Okay, let me go like this. The C, I'm going to let it be 70. And we're going to let this be the first one, 94.6. Now, that temperature was recorded at the initial time when she started. So we're going to let that T be 0. And we're going to let that be when the time is 0. If that's 0, all of this collapses to 1. So then it looks like we get, long story short, our A is going to be, what is that, a 24.6? Right, because we had A plus 70 equals to 94, subtract 70 from both sides. So again, that first piece of information, again, we let that be the starting time when time is 0. So then it collapses to A equals 24.6, right? So then let's plug this in and plug in the second piece of information that we have. So now if we let this be our A, we get this 24.6. E, we still don't know K. We're going to say negative K. Now the time has been, what, after an hour? So now our T is 1. You don't really need to write it. 70. And after an hour, the temperature was what? 93.4 degrees. Okay. So from here, it looks like we can solve for K. Let's try to solve for K from here. So we subtract 70. We have this 24.6 e to the negative K equals 23.4. Divide both sides, this e to the negative K equals 23.4 over 24.6, okay? Take the natural log on both sides. These cancel, this comes down. I'll go ahead and move the negative. So ultimately our K looks like it equals negative natural log of this 23.4 over 24.6. That's our rate. That's an exact expression for our rate. Okay, so we have an expression for our A. We have an expression for our K. So if we have A, we have K, we have C, we can solve for little t now. Okay. So let me plug this information in. So the temperature of the body. I feel like I'm missing something here. Rate of change. And see, I haven't used that and I'm still not seeing how to use it. We got our K, we got our A, we got K, A, C. Let me see. She also knows that the temperature of the room is 70. When did it happen? Oh. Oh, okay. All right. So if when the time is 0, it's whatever temperature she took, the 94.6. I think we have to pull another piece of information where we need the general temperature of the human body. I think it's like 96.8 degrees, something like that. I think that's the only other piece of information we need is like the general temperature of like a healthy living human body. And then we have everything work backwards. I'm just looking at the thing here. Yada, 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 yada. We got that right there. So to determine, now we're gonna need to determine the time of death. Assuming the individual had a normal body temperature, 98.6 degrees. That's the only piece of information we needed. So we kind of needed that. So I'm gonna just put it here. 98.6 degrees, right? Fahrenheit. That's the temperature of a healthy human body in general. Okay, so now with those pieces of information, now we can solve for little t. Okay. So I kind of want to duplicate this slide. Give myself some space. Duplicate. Come on. Yep, I'm going to work on this one. And I'm going to get rid of, I just need the blue highlights. So I don't need this. I don't need this. I don't need that. Delete. That's good. I do need this. I do need this. And I do need this. Okay. Everything else. Delete. And delete. Okay, I think we're ready to rock and roll. Let's give it a go. So I was like, yeah, there's something else we needed, and then it dawned on me we needed the temperature of a normal human body. Okay. So now let's plug this in. So we got this 24.6 times e to the negative. I'm just going to reference it as star. So next star. We're solving for little t. Our C was 70. That's the temperature of the room. Equals the 98.6, the temperature of the normal human body. Okay. So we can subtract 70 from both sides. We'll have this 24.6 e to the negative kt equals 28.6. Divide both sides by that 24. E to the power of negative kt. You're going to have this 28.6 over 24.6, okay? Now we take the natural log on both sides. Okay. These cancel, this comes in front. Okay. Keep working over here. So now we have the negative kt equals natural log of this 28.6 over 24.6, okay? And then ultimately little t, the murder should have occurred based on, this is an expression for exact natural log of 28.6 over 24.6 divided by, let me see, there should be a negative in here. Probably gonna resize this. Okay, our star is right here. Oh, it's a double negative in play. Okay, I'm gonna count it as a double negative. Get rid of that. So when we plug in our k, it cancels out this other negative, And we're left with the natural log of this 23.4 over 24.6. So then that's an exact expression. Then we just need to use our calculator. And we would imagine maybe a few hours before. I think that was noon. I think the coroner took their first temperature at noon. So we would anticipate it to be a few hours before noon. So let's see what happens. We should get a negative result because if noon is times 0 and it happened before, we should get a negative, right? Okay, let's see. So we're going to say the natural log of 28.6 over 24.6 divided by the natural log 23.4 over 24. Wait a minute. I think I made a mistake. 28.6, no, I think we're good. And then 0.4 over 0.6. Okay. No, I think we're good. 24.6. Okay, let's go with it. Get a negative few hours, negative 3 hours, right? So 12 minus 3, what is that, 9 a.m. in the morning? Somebody got to work and just had a bad day, right? Just one of them days like the movie with SZA and, what is her name? I'm so stuck on Aquila and Devi, and I know that's not her name. What is her name? Oh my God. Any other time I would know. Anyway, apparently somebody had a bad day, similar to that movie. Okay. So the time was approximately, I'll just put it as a negative 3.01 hours, which is like 9 a.m., approximately 9 a.m. That's interesting. We're gonna recap that. I know we got a little dicey for a hot second, but I remember the key piece of information that I knew we needed. Okay, so we got a result of 9 a.m. Let me just kind of check the prepared notes just to make sure before we launch into it. What time is it? We still got a solid 30 minutes. Okay. Yada, yada, yada. Let me just see the answer. Again, if you crunch numbers along the way, you have to write out the long decimal every time until you get to the end. Only round at the very end. If you round early, then it's going to throw it off. Approximately 9 a.m. Okay, let's just recap this real quick. So a little shindig. Did you guys have fun like watching the Super Bowl? I didn't watch it live. Like, I'm just not a sports person. I do have fond memories of like being a youth or being young, and like, our families would go to like Super Bowl parties, like at mansions and pool parties and all this kind of stuff. I don't know if we did the pool in this Super Bowl, but they had a pool there, and it was just big people. Now it's like everything's totally different, but so I didn't watch it live, and I'm the type I get more excited about the commercials than the game. And sure enough, I don't know if y'all saw this commercial. Oh my God! So like, I follow these content creators every night. And it's just always researching interesting aliens, stuff like that. And so one of them, everybody's been talking about the Super Bowl, but one of the ones I saw today, he was reviewing the commercials. And he reviewed the one with Seal as a seal. Then kissed by your, that shit was so funny. Oh my God. Seal as a seal. That jump was funny. It still makes me laugh. So if you get a chance, just hop on YouTube and type in Seal for the Super Bowl commercial. Man, that was funny. Especially if you know who Seal is. Because I always thought about that. His name is Seal, Anyway. So, okay. I just want to recap this. So, a body is found slumped over a desk at a study. The coroner arrives at noon, immediately takes the temperature of the body. So they arrive at noon. That's when our time was 0. And when they first took the temperature, it was 94.6 degrees. She waits an hour and then takes the temperature again and finds the temperature to be 93.4 degrees. She also notes that the temperature of the room is 70 degrees. We want to find out when was this murder committed. Now, I didn't even use the rate of change. I didn't use that one. I just used the model that they gave us. The T of T equals A e to the negative KT plus C. So we know that the initial temperature she took at noon was 94.6, and then 1 hour later was a 93.4. And C was the temperature of the room. So then we plugged in the first temperature, we plugged in the temperature of the room, and at that point we acknowledged that, okay, We didn't know our A, we didn't know our K, but that's when our time was 0. So because time was 0, that exponential expression became the number 1. So we just had A plus 70 equals 94. Ultimately, A equals 24.6, right? So we had an expression for A. So then we took this and plugged it back into the expression, and now we use the other temperature. So this is when our time it's been 1 hour later than, the temperature of the room was 70 and the temperature of the body was 93.4. So at this point, we have one equation, one unknown we could solve. The only thing we don't know at this point was the K, right? So then we used algebra from that point. So if you can get to that line on the bottom left, from there it's algebra with a little bit of exponential. This is still algebra. This is algebra from this point. Okay. So then subtract the 70, divide by the 24. That got us to here in black. Then we took the natural log on both sides. Natural log of E cancels. That allows us to bring this power down. And I went on and divided both sides by a negative. So that's where this negative came from. The natural log persisted from the previous example. And I just left it like this. I didn't crunch that number because I didn't feel like writing out that long decimal. I don't really like to do it, but again, if you want to crunch the number, you have to write out the long decimal, right? So if you crunch that, so then, and then we had to go and pull the information for the normal temperature of the human body, of a healthy human body, 98.6. So those 3 blue highlights were the 3 pieces of information that we needed. So we took those and plugged it into this equation. Let's see, here, here, and here. K, A, and then the 98 was the other side of the equal sign. Okay. So then once we had all that, again, we had our A, we had our K, we had the temperature of the healthy body, and we plugged all that in. You can see the A here. The K, I just referenced it as star instead of trying to write this repeatedly. So I just used the star reference, and then I plugged it in at the end. The 70 was the temperature of the room, and then the 98.6 was the temperature of a healthy human body. So at that point, we had one unknown, one equation we can solve, and then from here, it's algebra. From this point, it's algebra. Subtract the 70, divide by the 24, take the natural log on both sides. But then ultimately, we got to an exact expression for this. We crunched the number, and we got a negative 3 hours, which is what we anticipated, which implies that the murder happened around 9 a.m. So then, if there's some security footage either in that office or in the surrounding area, they can, watch the footage and say, okay, who was coming and going around that time? Yada yada yada. All right. That's another thing that'd be really interesting on YouTube, like some of these murder stories and like I watched one. There's a guy on YouTube. I don't even know his name. It's I don't know. He might be Middle Eastern or something, but he always just reviews these like interesting stories. And there was one of like these kids that scammed this billionaire out of crypto money. And I mean, for a while they kind of quote unquote were getting away with it. Like they successfully scammed him out of it, and they just started living large. Like it was about 2 or 3 of the guys. One of the guys reported the whole thing. Why? I don't know why you do that, but I guess he did it if he felt like they're going to get caught, he was going to use it to protect himself, which I think eventually he did. And then, so 2 of the guys were kind of low key. They didn't do any like crazy balling, but this one guy, I mean, he just went crazy. They ended up selling like, I think it was like $244 million worth of crypto, something like that, some ridiculous amount, either millions or billions. It might be billions, but it was a lot. And one guy was going ham. I mean, buying cars, giving out cars, like expensive purses to girls in the club. Like it was crazy. But then, I mean, obviously, so the way he got caught was, when it comes to like blockchain transactions, like when you're doing, with the transactions of blockchain, that's public. That's part of the security of blockchain is that it's public knowledge. And so they tried to like bury the transactions under like a whole bunch of minute tasks. And again, for a while it was working, but then one day, some guy who had also been scammed out of like blockchain money, when he got scammed, he decided to just make it a point to just not let that happen to anybody else. And he got an alert that said that there was this huge transaction on a blockchain. So he started investigating, and then that investigation that this one guy started is how they got caught. and they show like actual footage of the guy, of what the teenager, especially the one that was balling, buying everybody cars, all this. They show footage of him actually being caught. It was an interesting story, It was just interesting. So, I don't know. Anywho, okay, so we still got a solid. That's only 10 minutes. I think we're essentially done here. We did everything here that we intended to do. Meet with them at 7:30. Okay, let's take at least 10 minutes, if not a little bit longer, and go through some homework questions. Okay, I think this is all good. Okay, so let me see. I'm going to add a page here. Change the view to seamless. Let me see if I go here. So we won't stay all the way until 7:15, but I do want to hang out for like at least 10 more minutes. Give me just a moment right here. Let's go. Sign in. Oof. Allow. Right here. Yes. No. There it is. Let's go here. Here, you can minimize that. This, come on. This one. Yeah, like, it's just a lot of interesting things going on right now. Like with Trump, I can't really get a read on him. But I like a lot of things that he's doing. I know there's a lot of sinister things at play, but I do like a lot of things that he's doing. I like the stopping the men competing in women's sports thing, and exposing the money laundering that's been going on. I feel like if it were the Democrats make me nervous because Biden, man, he clearly was like taking money, like stealing, allegedly. I got to say that, but man, it was just like. And like they were spending money on just like stuff that had nothing to do with the prices in China, like millions and millions of dollars to just crap stuff. So it was clearly like a front when you got your own people here homeless and starving and hungry, and like nobody could find like a livable wage. Like we're spending trillions of dollars, the economy is getting worse, but somehow the deficit keeps growing. That means somebody's stealing the money. So that's. I set this one out because I couldn't really vote for Trump, but I couldn't support the Democrats either. So I just was like, you know what, I'm good. Let's pass go. I feel like, and Kamala, I couldn't read her either, like because I knew that Trump was not Trump. I knew that Biden was like the culprit for a lot of like chaos that was going on, and I just didn't know enough about Kamala to be like, okay, well, was she? And I kept getting the feeling that she would continue whatever Biden was doing, which I could not condone. The whole, men competing in women's sports, all the money that was being stolen, our tax money, they're basically, quote unquote, under duress, forcing us to pay taxes, but then we don't get a say in how the money's being used, And apparently, like, income tax is criminal in itself. Like, apparently there's no law that says that we have to pay taxes. Originally it was optional. And apparently, like, unless you're a corporation where you're turning a profit, that's the only thing that's really supposed to be taxed. But income tax, where we've already traded our labor wages, trading our energy, that's not a profit. That's compensation, and it's not supposed to be taxed, according to Kev from Real Nagas. So this is like, again, I'm not any kind of official anybody. You still have to do your own research. This is just the narrative, the story. It's really interesting. I still pay my taxes reluctantly until I figure out how to circumvent all of that nonsense. And then it's like when you start thinking about it, it's disgusting because, our income gets taxed, and then we got to take our money that's already taxed, and every time we do a transaction, that's taxed. You see what I'm saying? It's like, if we work for a company, any money that company makes is taxed. Then when they pay us, they automatically take taxes out of our check. And then every time we go to use this money, we got to pay taxes again. We got to take our money that's already taxed and pay taxes again every time we use it. And then they got the nerve to print money. So it's like now the little bit of money that we have left, after all this taxation, and then when they go and print the money, that causes inflation and that causes the value or the weight of our dollar to go down. And it's like, it's a clusterfuck. Like, are you serious? Like, for real? Come on. Like, it's criminal. It's criminal. Again, this is just how my opinions. You got to do your own research and decide for yourself and things of that nature. But it's, it's really interesting stuff. So, and now let Kev tell it, there are ways to become like sovereign and this other thing. And then he kind of always talks about like having one foot in the door and one foot out of the door. And I mean, honestly, he's like, okay, well, here's the documentation. If you go through it and you learn it, we can show you how to set it up. That's kind of how he always goes. Again, the channel is like called Real Nagas. But anyway, his channel is interesting. He always comes in on Saturdays talking about current events. Okay. Good. I'm a king of filling in time. But anyway, let's work a few examples at least from this section.
Excuse me, Professor.
Go ahead.
Did you see my message in the chat? I had left the Zoom on my phone. I had to rejoin it.
It's okay.
Oh, okay.
Yeah, it's
Thanks.
okay. I can check it now though. See if there are any others. Yeah, it's fine. Okay. So we left off on 2.5. We honestly have 15 minutes. I'm not going to use the whole 15 minutes. At least like 5 or 6. Maybe a little bit more. Okay. Let's just work an example or two from 2.5. Hey Google, give me a random number between 1 and 20.
Here's a random number, 9.
Okay, we'll look at question 9. So this question comes from section 2.5, question 25 from the back of the section. It says the decay rate, let me zoom in a little bit. Okay. So the decay rate K for a particular radioactive element is this. Hang on. K rate for a particular radioactive element is this, where time is measured in years. Find the half-life. They gave us the decay rate. We have the half-life formula, T equals a natural log of 2 over K. So we should be able to do the natural log of 2 divided by that 1.8% as a decimal. So let's see if that works. We're going to do the natural log of 2 divided by 0.018. 1 decimal place is 38.5. Okay, let's see how do we do. Nice. Okay, so we got lucky with that when they gave us the rate. They don't always give us the rate. Sometimes they give us other information and we have to find the rate before we can calculate the half-life. So again, we got lucky with this one because they gave us the rate. Hey Google, give me another random number between 1 and 20.
Here's a random number, 17.
17, right here. Let's see, for the scatter plot on the right, determine which, if any of these functions might be used as a model for the data. Okay, let's zoom out soon. It looks like it's some kind of decay. I'm trying to think if it's like exponential or logarithmic. Let's see. So, okay, like one of the things I'm trying to decide is like, okay, which way do I think that the asymptote is? If the asymptote is vertical, that would be indicative of logistic. If the asymptote is horizontal, that would be an indication that it might be exponential. And I'm going to say that the asymptote is a horizontal, like the x-axis serves as a horizontal asymptote. It looks like exponential decay, right? exponential decay. Exponential. K is positive. It looks like that second row 2 on the right. Yeah, because exponentials have a horizontal asymptote. Which of the functions might be used as a model? I'm going to think it's the exponential decay one, which is E. Let's try that one. Okay. So, and like, yeah, like the vertical asymptote didn't make sense. Because if you look at like how it's behaving, it's just like they're tapering off towards the x-axis. So it looks like it has a horizontal asymptote. If it has a horizontal asymptote, that would be an indication of an exponential function. If it were a vertical asymptote, that would be an indication of a logistic function. If we can identify something like that. Okay. Hey Google, give me another random number between 1 and 20.
1.
Someone she has some sass. 1. Let's go to question 1. All right. So use the graph and the transformations to sketch the exponential function, determine the domain and range, and wire intercept, and the equation of the horizontal asymptote. Okay. So transformations from college algebra 1, right? There's a total of 10 transformations. You have some rigid ones. You can move up and down, side to side. You have 2 that allow it to flip either vertically or horizontally. And then you have 4 non-rigid transformations that cause a distortion. You can either stretch it vertically or horizontally or compress it vertically or horizontally, right? So, it wouldn't hurt to review that. If anybody needs a review on that, just let me know and I can point you towards some information. Let me see. Okay, so e to the x. So we have a +5 on the outside of our base function. Our base function will be e to the x, all right, just a general exponential function. If we add that 5 on the outside of the base function, that's like adding 5 to all the y values. So it should move the final graph up 5 units. So it's just an exponential function. You have your horizontal asymptote that's been moved up by 5 units. Okay, so I'm going to click to enlarge the graph. Exponential is top row right. And I'm just going to click randomly in this graph, right? So this is a general exponential. We said we just take this. The base should already be E. I can't stop showing. Usually it's another part now. And then we just move it. We need to do a vertical shift up 5 units. That should be it. Again, it's not letting me. I'm just going to assume that the base is fine. It's usually another option there. I think if I zoom out, it'll show. Let's see. I'm just going to clear and just try again. This one, click. Guess it's not there. That's fine. We'll do a vertical shift up 5. Sometimes they want you to show the horizontal asymptote. I'm going to just go with this. Okay. The domain, right? So again, this is just a general exponential. I know it's a little bit zoomed out. The domain of exponential is all reals. So the domain of this is negative infinity to infinity. Negative infinity to infinity. The range, normally for exponential is 0 to infinity, open interval from 0 to infinity. Since this guy, we moved it up by 5, it's going to be the open interval from 0 to 5. So we get infinitesimally closest to 5, but we don't actually include 5. So we're going to say 5 to infinity. Why is it behaving like that? In a graphical sense, the range will be the very bottom to the very top. The domain is the very left to the very right. The wire intercept looks like a 6. So when x is 0, it's going to be 1 plus 5 because it's a 6. the horizontal asymptote is going to be y equals 5. Okay. All right, that's enough. Are there any burning questions, gentlemen, before we go separate ways?
No, but the test is
So
next.
I'll go ahead and make a comment. It opens up this Sunday. Yeah, and it'll be available. You can get full credit for the first 7 days.
Okay.
All of our assignments are unlimited attempts with the system set to take your highest score. Delete. Okay. Any other burning questions before we go our separate ways? So again, we did 2.5 today. Wednesday we'll be working on 2.6, and that'll close out chapter 2. Again, you can anticipate exam 1 to become available this upcoming Sunday at 11 a.m. For the first 7 days, you can earn full credit. It'll be due at the start of class a week later, basically. And then you can, again, with all of these assignments, you can work on the past the due date. But there's a late penalty if things are submitted late. Everything is unlimited attempts, and the system is set to take your highest score. And also, be sure to check your grade on Blackboard. It should be updating automatically. I kind of glanced at them before the start of class, and it seemed like it was working properly. So whatever grade you see in Blackboard, that's a grade that I'm going to be submitting periodically. That's the one I'm going to be using. So if it looks out of order, you need to bring it to my attention ASAP. Either email or call or text my office cell phone. Okay, so if there aren't any other burning questions, we're going to go ahead and end the session here. And from one beautiful mind to another, enjoy the rest of your evening, gentlemen, and we'll meet back on Wednesday, same time, same place to close out chapter 2. All right, guys, take care. Peace. Okay, let's stop the screen share. I think the chat looked good. I think it was the one. I think we resolved it already. It's okay. All right. All right, guys, take care.